Hello, my name is Boris Galkin, presenting the work Experimental Evaluation of a UAV User QoS from a two-tier 3.6 GHz spectrum network. UAVs have been growing in popularity in a range of applications in recent years. These include delivery operations, search and rescue, surveying work, and recreational flight. Uh, Many of these applications require the UAV to have an uninterrupted and reliable wireless connection back to the pilot. Next generation cellular networks are intended to provide this type of wireless connectivity to this new type of aerial user. A number of existing experimental trials have demonstrated that UAVs encounter significant connectivity and performance issues when attempting to connect to conventional cellular networks due to issues such as beam antenna misalignment and significant interference due to an obstructed line of sight channels. Uh, a number of works have begun looking at 5G UAV connectivity and performing experimental trials of this type of performance. Generally, the existing literature tends to focus on the connectivity between UAVs and macrocell infrastructure. UAVs, because they fly in the air, they have the strong unobstructed line of sight channels to distant infrastructure, which means they can always reliably detect and connect to uh, faraway base stations. Now, having said that, 5G and beyond cellular networks will heavily rely on small cell infrastructure in densely populated or urban areas. These small cells will provide additional coverage and additional capacity to service demand hotspots. UAVs that will be operating above these urban areas will invariably come in contact with small cell cellular infrastructure. And this motivates this current experiment. We are interested in examining the performance of a UAV user when it connects into a two-tier cellular network, which includes small cells positioned close to ground level. Now, this is a diagram showing our test bed. We performed these experiments in the Smart Docklands district of Dublin City in Ireland. We've identified two locations where we would fly a drone. These are marked in green and are denoted as North Wall Key and Grand Canal Key. There's an experimental two-tier test bed deployed in this area, which consists of macro cells with massive MIMO capabilities and small cells shown in white, which wirelessly backhaul into the macro cell tier. And the UAVs, when flying in the green areas, would be connecting to one of these tiers. So this is an urban area with large bodies of water that make it safe to fly UAVs, but which are surrounded by buildings ranging in height between 20 meters and 80 meters, which will create shadowing for the cellular signals. The testbed operates on the 5G 3.6 gigahertz band in the B42 channel. The massive MIMO macro cells are equipped with 64 element antennas. The small cells are equipped with 4 element antennas, which apply 2x2 MIMO and which wirelessly backhaul into the macro cell tier. The macro cells have a maximum transmit power of 49.9 dBm and the small cells of 25 dBm. Here's another photo showing our experimental location. In the bottom right, we see a photo of the drone. This is a DJI Matrice M300 with a Google Pixel 3 handset mounted on top. In the background, this is the Grand Canal Key location where the drone will be operating and flying. And on the left, the red X marks the approximate location of the Trinity Center macro cell. It's hidden behind buildings in this photograph. So the experiment will consist of flying the UAV with the mounted handset back and forth across these two areas at 10-meter height intervals between 30 meters above ground and 120 meters above ground at a speed of 8 meters per second. The handset will operate in idle mode and in dedicated mode. In idle mode, it will simply monitor the signals coming from the cellular network, and in dedicated mode, it will be actively downloading data through the cellular network. We will measure the reference signal received power, the reference signal received quality, and the signal to interference and noise ratio from the handset when it is connected to the cellular network. In dedicated mode, we will also additionally measure the downlink throughput that's achieved from the connection. We will also keep track of any handover events if they occur during the UAV flight. So this is the first set of our results showing the UAV handset performance when it is in idle mode across varying heights above ground. The two lines in red and blue show the average values for the given height for the Grand Canal key location and the North Wall key location. It should be noted that in the Grand Canal key location, the UAV handset was always connected to the macro cell located at the Trinity Enterprise Center, whereas at the North Wall key location, the UAV was always connected to one of the small cells on the ground. So this is performance. It can be seen as the performance of the macro cell tier and the small cell tier in blue and in red, respectively. And what we see is that as we increase the height above ground, the overall performance appears to deteriorate for both the RSRP and the RSRQ. Increasing the height of the UAV above ground increases the distance between the UAV and the small cells located at ground level. Also, increasing the height of the UAV above ground results in potentially poor beam tracking and alignment from the macro cell located at rooftop level. So looking at the SINR, we also note a significant performance deterioration for the macro cell at the Grand Canal key location. This result corroborates the reports from the existing state of the art, which suggests that UAVs experience significant SINR deterioration at greater heights above ground due to strong interference received through unobstructed line of sight channels. And we observed that there is almost a 15 decibel SINR drop going from 30 meters to 120 meters above ground. What's interesting to note, however, is that for the small cells at the North Wall key location, the SINR appears relatively consistent with no noticeable overall trend in the performance change as the height above ground increases. Looking now at the dedicated mode, and we see somewhat similar behavior for the RSRP values, where the North Wall key and the Grand Canal key RSRP measurements are somewhat similar in the dedicated mode as in the idle mode. The RSRQ values, however, for the Grand Canal key location drop significantly in the dedicated mode compared to the idle mode. Looking now at the SINR values, and if we compare this to the idle mode performance, we can actually see that there's a slight improvement in the overall SINR for both the Grand Canal key and the North Wall key locations, possibly due to how MIMO is applied when the handset is in dedicated mode. But we still overall observe that there is a performance drop as we increase the height above ground for the UAV. And looking at the downlink throughput, we notice that there's a significant drop in the throughput values for the Grand Canal key location as we increase the height of the UAV above ground. At 30 meters, the UAV is able to receive approximately 70 megabit per second data rates. At 120 meters, that falls to 40 megabits per second. This is quite an interesting result. Even though the UAV, increasing its height above ground, is able to establish unobstructed line of sight link to the macro cell that it's connected to, because of the fact that the macro cell applies massive MIMO, it's able to make use of multipath channels connecting to the handset. And if they're at larger heights, when there is a single dominant line of sight link between the macro cell and the UAV, the spatial multiplexing that can be offered by the massive MIMO antenna it appears to have less of an effect. Now, looking at the downlink throughput for the small cell tier, however, we see that the throughput is relatively consistent across the entire range of heights, floating at approximately 35 megabits per second between 30 and 120 meters above ground. Now, looking at the handover behavior, we first report that there were no handovers occurring in the Grand Canal key location. The UAV was connected always to a single macro cell at the Trinity Enterprise Center. With the Northwall key location, where the UAV was connected to small cells, there were handovers occurring between the small cells. However, there were no handovers occurring between the small cell tier and the macro cell tier. The UAV was always connected to the small cells. The handovers were triggered by the A3 event, which monitored the RSRP changes from the small cells. The A3 offset was set to be 2 decibels. The hysteresis margin was at 1 decibel, and the time to trigger was set to 128 milliseconds. Now, referring back to a diagram of our experimental testbed map, we can see that the UAV flying in the Nordwall key location connected most of its time to small cell 478 and small cell 412. It barely ever connected to cell 207 and never connected to cell 92. These two cells had their coverage areas shaped to not provide coverage over the area of the water where the UAV was flying, and as a result, it would not be connecting to those cells. What's also interesting is that at the larger height above ground, the UAV would actually connect sometimes to the cell 3.6 GHz, which is approximately a kilometer away from the measurement area. So we presume that the UAV was receiving strong side lobe signals from that small cell at the greater heights, and as a result, it was able to connect to that small cell even though it was quite far away. Now, looking at the handover rates for the UAV at varying heights, we observed quite a significant handover rate fluctuation. So, for example, when increasing its height from 50 meters to 100 meters above ground, there was a quadrupling of the handover rate that the UAV experienced. Despite this fluctuation, however, the actual handover rates that we measured were quite low. At most, the UAV would have an average of 30, one handover every 30 seconds. So to summarize, we observed performance degradation for the UAV as we increased the height of the UAV above ground, both when connecting to the macro cell and the small cells. In particular, this performance degradation was noticeable for the macro cell tier. And this is quite an interesting result. The wireless community has reported on UAVs experiencing performance degradation at larger heights in the past. However, many of these analyses and measurements were done for LTE networks, which did not apply technologies such as massive MIMO. Massive MIMO has in fact been suggested by researchers to be a possible solution to the UAV connectivity issues that have been reported. However, despite this, we observe that even with massive MIMO, there is still very significant performance deterioration as the UAV height above ground is increased. We observed that small cells can maintain a relatively stable performance across the tested range of heights with handover rates that were fairly manageable. So the data throughput was very consistent for our measurements, and the handover rates, even though they fluctuated, were still quite low with a cap of about 2 handovers per minute. In future work, we intend to continue this analysis and expand our measurement campaign. We intend to explore further the relationship between some of the network parameters and the resulting UAV performance. In particular, we're very interested in the performance of the UAV when it's connected to the small cell tier, and looking at how the handover parameters for the small cell tier will affect the resulting UAV mobility behavior. Now, a sample of our measurement data set is available on our website at the link provided. The full data set is available on request. If you just send an email either to myself at galkin@tcd.ie or to Conor Duff at cduff@densair.net. This work was supported by the funding from National Natural Science Foundation of China and the Science Foundation Ireland. And this experiment was carried out in cooperation with Densair Limited and Smart Docklands of Dublin City Council. Thank you for your time.